Okay, time to get started. So let's see here. We're recording, at least for the moment, fingers crossed. Okay, so picking up where we left off last time, we were talking about triple integrals. They're basically like double integrals, just a little bit more so, right? I mean, 3 dimensions instead of 2. 3 nested single variable integrals to make an iterated integral instead of 2. But basically the same idea. The whole is the sum of the parts. We understand some problem that we're interested in by chopping it into little pieces and adding them up. It's morally kind of equivalent. Okay, so all that said. Oh, by the way, don't forget attendance quiz, attendance code. You've got another minute 12 to get that submitted. Okay, so just another example. Again, the trickiest part of triple integrals is figuring out what the bounds are when you rewrite it as an iterated integral. That's where it's just geometrically challenging, artistically challenging, and so lots of examples for that purpose. Okay, so proceeding. Suppose our domain for our integral is the unit ball. Right, now it seems like an easy one, right? It's a barnyard variety geometric figure. It's actually going to be a little bit ugly. And here's the way to do it. Now, the brute force direct way to do it is, for example, and let's suppose we're going to put our differentials in this order right here. X being on the outside, we slice perpendicular to the x-axis, and that gives us these sort of disk cross sections, and then we slice up that disk. Next, perpendicular to the z-axis, giving us, if you think about horizontal slices like that, then that gives us slices that are little line segments like that. And you think about start and end and all that business. You can follow it through that way. I think it's probably a healthy exercise to give that a try, right? But let's think about the easier way to do it. And what I think is much easier is to kind of copy this idea that we did in the previous example, where we've got this point of view of projections, right? And if you can identify what I'm going to call a good projection, the problem just kind of unfolds very conveniently. Now again, you can slice and dice if you'd like. I will point out the art on this is harder than it looks. Drawing these figures is a little bit challenging, right? But look how easy it is if we think about projections. Now I've got x and z on the outside. Our rule for the projection is that whichever 2 variables have differentials on the outside, whichever 2 integrals you're doing on the outside, that's the coordinate plane that you're projecting to. So, what is the result of projecting the disk into the XZ coordinate plane? And not hard to persuade yourself, I think, that you get this unit disk in the XZ plane. And now I'm going to leave as an exercise for y'all to think through on your own, but if you just have the disk, unit disk, in the XZ plane, as we have over here, the bounds for that are that. Now again, make sure you can do that, but that is just a kind of double integral analysis. Think about the range of values for x, and then you look at an x slice, 2-dimensional pictures. Not that much to it, really, right? But again, good one to think through. Okay, so we're 2/3 of the way done. Right? This projection point of view is super valuable. It's not that artistically challenging to persuade yourself that a sphere projects to a disk, and it's not that challenging to slice up a disk a la double integral methods, and it's 2/3 of the way done. It's pretty awesome. So, reminder again, the next step is to think about lower bounds and upper bounds in the direction of the remaining variable. So our remaining variable is y, and so for a given point, for some given value of x and z, you imagine some point in that projection right there, you want to think about how y varies as I go, from the left side to the right side, right? So on which surface is our starting point always going to be? And I think it's a pretty easy pitch. We're always going to be in what you might call the Western Hemisphere. Right? That's where the starting point is always going to be. It's kind of on that left hemisphere. And I think it's also not that difficult of a pitch that where you're going to end up. That right endpoint is always going to be in the Eastern Hemisphere, right? This right side hemisphere. Those surfaces have easy equations. You could straight up solve for y and get those equations. Obviously the green one has y negative. Obviously the red one has y positive, right? And so not too hard to solve for y in those equations, and that gives you that bound. And I thought I had changed colors. Oh gosh. There we go. And that bound. Okay. So this projection point of view is really nice, right? It saved us what I would call a difficult slicing, visualizing, drawing challenge that we would have otherwise been faced with. Okay. So I hope you like it, and I hope you'll use this. Another example. Now this is another one that is geometrically challenging and artistically challenging. I'm going to start off by just the art side of it. So here, our question, we've got this region that's defined as being bounded by 5 separate planes. Now in general, if I were to just give you 5 random planes, right, and ask you to find the, understand and draw the resulting solid that is the unique region bounded by 5 random planes. Oh my gosh, that is really, really hard. I don't think I could do it easily, depending on what the planes are. Super challenging. That's not what we're looking at here. There is something particularly convenient about these planes. In particular, there is a set of 3 of them in which there are no y's anywhere in the equations. And I'm going to remind you all, flashing back to chapter 1, whatever section, 1.5, I want to say, about lines and planes. If there's no y's in the equation, then the resulting planes are parallel to the y-axis. And so this is a tremendously convenient little foot in the door. What it means is, since I know these planes are parallel to the y-axis, I can understand any one of them. Let's take, for example, z equals x right here. I can understand what that plane looks like and think in terms of how to draw that simply by drawing it first in the xz plane. Well, that was easy. Right there in the xz plane, z equals x, nothing to it. And then just realizing, okay, well, yeah, but this is a plane. It's a plane parallel to the y-axis, so we'll just drag parallel to the y-axis. Right? And likewise for these other lines, planes, that we are going to view first as being lines in the xz plane. Oh, come on, I can do better than that. Nothing to it. Right? Easy to draw lines. And then realize, obviously, very convenient to see that these are bounding this triangle. That's not geometrically challenging. Right? And then, but all of this business has no y, so we're going to drag parallel to the y-axis, and that's going to give us kind of a prism. Oh gosh, let's see here. There we go. Kind of a prism, like so. Is everybody on board? This is a neat move, right? Now again, you got to put this into your arsenal, your bag of tricks, your toolbox, whatever you want to call it, and be on the lookout for this sort of thing. It's very, very helpful little tool. That said, now there are 5 planes, and so I do have to also think about y equals 0. Okay, well, y equals 0 is that plane. Okay, how does that plane interact with this prism that we've just made? Well, it's pretty clear. It's just going to cut through the prism like so. And now the one that's a little annoying. This last one here, this is highly angled plane, right? It's not parallel to anything. So you can understand this by thinking about the intercepts. the X, Y, and Z intercepts, and then think about, how that cuts through like so. And now how does that angled plane, how does that cut through our prism? And, geometric appeal, I'm going to say, and we get a face that looks kind of like this. Yeah. By the way, if you have a little trouble with this last part here, how do I understand how that plane intersects with our existing thing? You can think about the points of intersection one at a time. So for example, this point right here, if you want to understand that point, well, it's in this plane, of course, but I can see it's also in this plane, which is that one. And it's also in, thank you, picture. It is in this plane that has that equation. And again, if you want to understand where that point is, then just, let's see how to, then just solve for it. Not that hard to do. The numbers work out pretty conveniently. Okay, so we got ourselves a picture. Now, again, the art on this one is a little challenging. That's why I spent a little time talking about it. Again, keep in mind that is kind of part of the problem. When you have a question like this, figuring out what your shape looks like, again, that's part of the problem, right? So you got to be ready to face that challenge and come up with a good answer based on these kinds of techniques. And being able to draw is unavoidably helpful to that end, right? So I remind you, please take your drawing skills seriously. This is something that is just it's gonna matter, right? Definitely. Okay, now let's talk about how to slice it. This one is a tricky slicing. And of your 6 options, this is the only way to do it that doesn't slice through corners. Now, so you gotta watch out for this kind of thing. This is the nature of the world, right? So this is not me trying to be a jerk. This kind of thing happens naturally in the real world. So you do have to think strategically when you find yourself looking at a 3-dimensional solid. You want to do a triple integral and you're thinking about how to slice it up. Think it through, right? And so, for example, let me just show you how it would fail if I were to do, for example, whatever dy. Let's put our dy on the outside and see how this goes south. And what happens with dy on the outside? Here's what your y slices look like. Doesn't seem so bad. Right up until you hit this corner. And now your slices look fundamentally different, right? And so you're going to have to take, can I even draw this? Oh, this may be, let's give it a whack. Something like that maybe, right? So you have to start a whole new iterated integral when you get to that corner. And then you hit this corner. After which point your slices will again look different, and they'll start to look, let's see here, more like kind of this or something. It's hard to draw. So, crash and burn failure, right? And again, there's really only one way to avoid this kind of ugliness, and that is this particular order here. Now, how did I come up with that? Well, I spent some time thinking about the different ways to slice and failing over and over and over again until I found the one, right, that works. Tedious. We don't want to do that. I assume that's not your idea of a good time, right? So how can we better deal with this? What's the more efficient way to think about this? And again, I'm going to come back to projections, right? So let's think about in which direction can I do a convenient projection and have everything just work out all convenient and stuff. And here it is, in the XZ direction. If I project into the XZ plane, notice I get a triangle. So I get a nice domain for my outside 2 bounds. Triangles are no big, right? Notice further my inside variable y as, from any point in that projection, in other words, for any value of x and z, notice that my range of values of y starts at a point that's always on this surface, that always has the same equation consistently. It's one of our requirements for a good projection. And notice that it ends at a point like that. That is always on this face, that always has the same equation. And again, consistency. Right? So solving for y on that surface gives you your lower bound, and solving for y on this surface gives you your upper bound. And boom, it just all fell apart. Nothing to it. How we doing? Is everybody on board? Okay, let me show you what it will look like if you try to project in a poor direction. Now, no particular reason, but let's think about a projection into, let's say the YZ plane. And this is going to actually look pretty decent at first. If you project into the YZ plane, let's see here, it's going to be something kind of like this. There's your projection into the YZ plane. Right? Looks fine. No problem. Where's your lower bound surface? Your lower bound surface is going to be this face back here. Again, all good, no problem. Here's where it goes south. If you ask where's your upper bound surface, it is unfortunately two separate surfaces. And so we fail the consistency, right? There's no consistent equation that allows me to solve for my upper bound. I'd have to say, well, for some of those points in the projection, it's the surface on the left there, and for other points in our projection, it's the surface on the right, and so, well, you're going to have to break that up into two pieces, and again, no one wants that, right? That doubles your work, at least. Not to mention the fact that you'd have to figure out how to break up your projected domain. So this is what I would call a bad projection. And that's why I didn't do it, right? And again, notice no such problems here. Okay, so when you find yourself looking at a three-dimensional solid, again, it's a really healthy exercise to think in terms of, well, if I project, which of the three different directions that I can project, which one looks good, and which one is going to have that consistency and convenience that we're looking for, and do that one. All right. Here's another example. Another great example of a projection. Let's take a quick moment to recognize what an ugly shape this is. Right? It's actually really bad. So for example, we've got, let's see here, this surface, which you can see is a paraboloid, no problem. Chapter 2, make sure you're good with all that stuff, of course. And then you got this surface, that is another paraboloid, which is going to look something like that. And again, chapter 2, make sure you're good with all that. And the region that is bounded in between is going to be this weird, very hard to draw, I just don't know what to call this thing. That's a weird shape, and anyway, it is what it is, but that's our domain. Okay, so how to slice that up. And here's where it gets bad. You might say, look, I think the easiest kinds of slices to take would be perpendicular to the y-axis because those slices are all discs, but they're not, right? Things get weird after you hit this. It's not a corner exactly, right? But all of a sudden, nevertheless, the shape of the slices changes into annuli, right? That's not a disc. There's kind of a gap. There's a hole in the middle. Right? So if this is what one of my slices were to look like, then I would have to next step figure out how to slice up that slice. And well, it's going to be, I think you can probably see it's going to be 4 separate regions. This is a catastrophe. This is a horrible idea. We're definitely not going to do that. Okay. You could try to slice in a different direction. Yeah, absolutely. And then here's what you get to deal with. And I'm going to do my best on this. Honestly, I'm not throwing it. But it is very hard to draw slices in a different direction. So for example, okay, here we go. I think, I need pencil. I think it's going to be something kind of like that. Right? And that's challenging. It's hard to do, right? And then again, keep in mind, that is what you are then going to have to slice up next. And it's hard. And, if only artistically. So, highly undesirable. But let's think about it in terms of projections. Now, you look at this shape, and I think it's a pretty easy pitch that the projection in the XZ direction is not going to be bad. Details, we'll figure out exactly how to understand that, right? But that's not bad. And then, for a given point somewhere in that domain, pick some point there, and think about what's the range of values of y. Well, y is going to go kind of, if you will, sort of like this. It's going to start at some point there that will always be on that surface every time. And then it's going to end at a point, let's say something like that, which again will always be on that surface every time. So, what would have been artistically super hard to deal with, now it's actually not that bad at all. We just got a couple of details. Sure. Right? We've got to figure out what is that orange projection domain. We're going to have to slice that up. Yeah, fine. And then I guess I am going to have to solve for y in the green equation, and I'm going to have to solve for y in the red equation. Okay, well that was easy, right? Already solved for. So not that much left. So again, a geometrically very challenging question turns into an easy question. Yes?
Since we're projecting in the x and z planes, does it matter like the orders between like the x and the z?
That's a great question. You have your choice. So that's not to say that it doesn't matter, right? It matters in the sense that, make the choice that's going to be easiest, right? And so in this case, our projection, I think you probably see it coming, is going to be a disk, right? And that one doesn't matter, it's highly symmetric, so go crazy, do whatever you want, right? But yeah, sometimes it really does matter. Actually, a pretty good example of that is if you look back to here, right? This projection down here, right, is much better dealt with z on the outside because that slices it like so. Whereas if I had sliced the other way, this same shape, if I had put my x on the outside, right, then I would slice through a corner. Exactly. Is that cool? Yeah. So yeah, always think strategically, always do what's going to be most convenient, basically, for you. Okay, so a couple of details. Most of the algebra I'm going to leave for y'all to think through. Again, y'all are good at that sort of thing. You need to be good at that sort of thing, so make sure you can do it. Let's think about how to understand this shadow, and I claim the shadow is understood by what it's surrounded by. What it's surrounded by is literally the shadow of that curve. That curve is the intersection of these two surfaces, namely, again, our lower bound surface and our upper bound surface. Right? So if I want to understand our domain, our new domain, bounded by that purple curve in the XZ plane, what I need to do is take this algebra and find the resulting relationship between x and z. And that relationship between x and z I get by recognizing that these two y's need to be equal, and that means that the things that those y's are equal to need to be equal, and that's easy to solve. So no big. There you go. Everybody okay? Okay, details. There's the final answer. Make sure you can do that. Okay. So that finishes triple integrals. By the way, let me recognize one thing before we go on. Actually, this example here, the big punchline was think about projections. This example here, the big punchline was think about projections. This example here, awesome with projections. Likewise, this one, right? So one might be left with the conclusion that you should always think in terms of projections, and I think that's an overstatement. I like to show examples of thinking by projection because it's these more subtle sort of method, right? But this kind of slicing here, where you literally slice and then slice up your slice, this should also be something that you always have ready to go and that you can use, as appropriate. Anyway, for your consideration. Okay, moving along. So, yeah, change of variables. This is a really big idea. Top 5 most important big ideas in the course. And roughly speaking, the idea is that if there's something you don't like about your integral, write it in terms of different variables. Maybe it'll get easier, right? This is going to be bonkers powerful in various different ways that we're going to see over the next week or so. By the way, section 5.5 is a monster section. I don't remember the exact number of pages, but it's a lot. And it's going to take us a good solid 3 days to get through it. It, I think, should be split up into 2 separate sections, at least, and maybe 3. But anyway, doesn't really matter, I suppose. But anyway, this idea of rewriting in terms of a different variable is going to be a huge idea for us, and we've already seen it before. So I want to start by reminding you where you have seen what is really, in fact, change of variables previously. And that is the single variable substitution rule. Now, y'all have probably thought of the substitution rule as a formula. This is the formula. That's, when it comes time to plug and chug, okay, yeah, I suppose it's handy to have a formula. You might have thought of it as a technique or a here's how you do it. Okay, cool, right? And usually that's thought in an algebraic way. And there's nothing wrong with that either. I do want to give you a different point of view on this. Again, I always have an ulterior motive. When I give you a different point of view, it's because the different point of view is going to extend more naturally to a multivariable setting, which is, of course, what we're actually here for. So here's the new point of view. And that is to think of this kind of geometrically. When I write down an equation like, let's see here, x equals g of t, yes, that is algebra, but also I can think of g as a function that takes t as its input and gives x as its output. T in, x out, and g is a function. So let's think of it as literally going from a domain written separately on the left to a target written separately on the right. And it's going to be very helpful to think of it in this way, unfamiliar though that may seem. Okay, so a couple of big ideas that I want to talk about related to what we just wrote down. First is the idea of a pullback, and I'm going to come up to some blank space up here and give you an easy first example of a pullback. This is no big deal, but let's suppose I have, again, I want to be in pen mode. Pen. Yeah, there we go. Okay, let's suppose that my relationship is that x is g of t, and that this formula is, t squared e to the t, whatever. Some formula like that. Right, so again, t is the input, and then x is the output. Okay, so now I draw the arrow this way, because, that's the way the function's going, right? We take point in, it goes into the function, we get a point out, and that process is left to right. Okay. Alright, so here's the thing. Points go left to right. The slightly counterintuitive but ultimately very familiar twist on this is that expressions go right to left. For example, if I have an expression here, sine of x, I can pull that expression back to rewrite it in terms of t just by plugging in. It's literally just plugging in. X equals that, plug that in there, and I get sine of, of t squared e to the t. Right, so a little bit counterintuitive. We think of functions as going left to right. We draw them going left to right, but when we do, while points go left to right, expressions, the act of plugging in,